Hey there, it's Max. This is Overlapping Chunks Exercise 1 Solution. So, I'm going to explain what we're supposed to do for this. Based upon this image, we're going to look at the source code for this. We're going to look at start.py, and then, of course, we're going to write the solution and look at this in GDB. And then finally, we'll go through the complete visual representation of this. So as I talked about before, we're going to use a buffer overflow in the chunk first to corrupt the size of the chunk second. To then, when chunk second gets reallocated as chunk 4, it will then corrupt the string in the chunk third using a buffer overflow again. One thing that's fairly good question is, well, Max, if we are just using one buffer overflow to get another, then why are we doing this? That is a good question. But a lot of times in exploitation, you get a very small primitive. There's a very small mistake. You can write 3 bytes out of bounds. You don't control the bytes being written, but you can write out of bounds. And a lot of times in exploitation, you need to take that smaller primitive and violate something else to give you a bigger primitive. A lot of exploits are, grow and grow and grow. I think a lot of the browser exploits are that way. In particular, where they go from a very subtle race condition into eventual rewrite primitive. So gaining steam in terms of primitives is a fairly common thing, but I think it's a fair question to ask. So with that, we're going to look at the start.py file. And I don't need to turn off my camera again. There we go. So, like we talked about before, the buffer overflow is right here, and we want to corrupt the size of the chunk second. I think it's easiest to see how many bytes we need to write by looking at this visual right here. So with the chunk first, we have the prev size and size, and then we start writing to this chunk data section. So starting point. Now, this is going to be hex 30 bytes. The chunk is hex 40 in size, but the data we're actually writing is hex 30. Yeah, it's hex 40 in size. Cool. So we need to go hex 30 bytes, and at that point, we're at prev size. So prev size is 8 bytes if we're on 64-bit, like this course is supposed to be done in. And then that gives us the point in which we're actually at the size. So 30 plus 8 gives us hex 38. So that means that this first value is hex 38. Now for the next one, I think we could look at this dynamically, or we could look at this looking at source code. I'm going to look at dynamically because that's more fun. Why did that crash, I wonder? Did I already solve this in here? I don't remember. Oh yeah, I wrote a bunch of A's. That makes sense why it would crash. Okay. I think live debugging is valuable, so I'll probably keep this in. So I wrote to the wrong file. I have a local copy and a remote copy, so I just wrote to the wrong one. But yeah, this is hex 38, and then this will write to the actual chunk size. So if we just didn't write this hex 38, if we wrote hex 20, and we didn't use the buffer overflow, and now we went to this, we can see what this chunk actually would be in terms of size. So look at the heap. We can do print second, and we can see what this chunk would be. We can see that this chunk is indeed hex 100. And of course, it has the prev in use bit because the other chunk is in use. Cool. So now we know what that chunk actually is. But what do we actually want it to be is the next question we have. And I think the easiest thing for this is knowing what actually is necessary. You can exploit a chunk and put a fake chunk in there, but the thing is, if you can't get it back out, it's useless. So in terms of heap exploitation, heap feng shui, it is important knowing what allocation sizes and things you have at your disposal. And in this case, the chunk size we have is 150. So now we have a chunk, we know our target has to be 150. That's the only allocation in the rest of the program that we want. So this chunk then has to be hex 150 in size for the fixed size of it. Because again, it's the only thing that's there. If it's not that, then it doesn't really work for us. Cool, so we have a fake chunk of hex 150 now. Now if we start this up again, and then we start looking at the breakpoints to see where stuff's actually breaking at, we see this this breaks right before the free. So if we look at the heap, now we can see that this chunk size is indeed hex 150. And now things are kind of corrupted because I think that Pwnybug will look at the chunks that are below it and actually go up the heap in order to find the proper chunks. So if you think look weird and look corrupted, that's probably why. So now if we continue, we see that this chunk size is hex 150, again, even though it's clearly not. And if we look at the variable fourth, if we go one more, we can see indeed that this is that 150 size chunk that we wanted all along. But it is also the pointer for second. So now second and fourth are the same. And this is exactly what we were trying to do. We were trying to corrupt second to be bigger than it actually was to work for an allocation that it shouldn't have. So we've successfully allocated a chunk that's too big. Or it's too little, for what we were asking for. So now if we go back to start.py, we need the last to do is this hex 1 right here. So we need to get to the point of Steve Jobs. So if you go back to our diagram here, I think this is, again, really helpful. This is the target string. It's within this chunk data that's right here. So right now, our new starting point that we're trying to calculate this for is right here. We're starting at this 10 bytes, or 16 bytes into second. So even though it was hex 100 in size, now it's hex F0. And then we need to go through both prev size and size, which is going to be another 16 bytes, which puts us back at hex 100. At that point, we are within the chunk data. So if we go back in here, we do start.py, this is just hex 100. And if we run start.py, if I could type the word Python, we just do continue. We can see here that the string of the third chunk is indeed Steve Jobs, which means that we've successfully completed this challenge, which is fun. Cool, so now I'll give the visual representation that I always do. I'm going to turn off the video because where the diagrams are at. So the vulnerability is a buffer overflow, like we talked about. The chunk first can write too many bytes to go into the chunk second. That's the initial foothold primitive. Now, if you just write this with all A's, it will just crash because you're writing too many bytes. And that's what I showed before. When it was crashing, I didn't understand why. That was the reason why. It's because it was writing a bunch of A's to the sides and I didn't know what to do with it. So the actual amount of bytes prior to the size is that first filler. So it's 16 bytes from the chunk to memory of first. It's hex 30 bytes until second, and then 8 more bytes to find the size. So it's hex 30 plus hex 8 gives us hex 38 in size. At this point, I think it's good to go through the calls to malloc and free to know what's going on. Very beginning, we have a bunch of calls to malloc, one hex 40, one hex 100, one for hex 50. And then we free second. If we allocate another chunk for the hex 150 or the fourth chunk, then it will allocate underneath that using the data or the memory left in the top chunk. However, we want it to be the chunk second. So the only allocation that we have left is at hex 150. So we're going to set the size of the chunk second using our buffer overflow to be hex 150. And now, when we set that, if you do that same process again, this will overlap with the chunk third we talked about. If we now look at this with the allocation or ordering we showed before, then it's a totally different view. When we free this and it's corrupted as hex 150, now the chunk fourth is used, and that's the cool part. So the chunk fourth and the chunk second, the same thing, but now it sits over the top of chunk 3 when it gets allocated. At that point, we need to write hex 100 bytes. When I'm thinking about getting to the next chunk of the actual data section, I just always think of the chunk size, because you're doing a plus hex 10 and a minus hex 10. It's kind of annoying, and they counter each other, so you can just ignore that effectively. So finally the print happens, and this in Houston, you've just been pwned. And we got this working, which is really fun. So to recap on this attack, we're going to corrupt the size of a chunk, we're going to free and allocate the chunk, and we're going to use that to cause havoc. So that's the exercise. There's only one exercise in this one. We do talk about nmap chunks later, but hope you guys enjoyed it. Thanks.